How are you with 3D modeling though?
In what program?
CATIA?
I have never used CATIA before. I didn't even know CATIA existed before I started working here. And then I was teaching finite elements, and students were asking me that, can we import CATIA into ANSYS? I'm like, what the hell is CATIA?
Yeah, honestly, I use SolidWorks at work, and it's like really frustrating when I know I can do something in SolidWorks that I can't do it with CATIA. Okay.
Yeah, apparently it's used in aerospace a lot.
Yeah, the bigger like system level companies use it primarily.
I see. Yeah, that's what I've heard.
Yeah. Like if you work at a company, like I work at like a quick component level company where it's like smaller, components that have, I guess, more intricate geometry. SolidWorks is good, but when you have like 1,000 components of something that's like a wing or something like that, then CATIA ends up being better for those kind of like the drafting of it a lot better.
I see. I see.
Yeah. So I missed class on Monday. I don't know if you noticed. I was taking my parents to LAX.
Okay.
I was like, I'll watch the lecture when I get back.
That's fine. You don't have to. You don't have to tell. You don't have to tell me.
No, it's I'm just saying because I didn't get a chance to review I wanted to watch the lecture on Monday, so I'm mostly prep. I didn't get a chance to. So.
Okay. Yeah, we kind of finished up. We finished up the last lecture notes, and then we're doing our next kind of MATLAB thing.
Okay.
And so we
introduced the projects. I saw all that.
Yeah. Today we'll talk about the project. I didn't talk about the project on Monday.
Okay, you just like kind of put it up there.
Yeah. I just said I'll have it ready by Wednesday, and we'll talk about it Wednesday.
Okay. Am I gonna be completely lost today?
No, because I mean we just started this, and so we kind of just barely got anywhere on that, and so you can just kind of follow along with the code, and so I'll kind of write this kind of along with you guys. Kind of the same thing with the frame code, except this is a bit easier than the frame code.
Okay.
Yeah.
Yeah, I'm still gonna watch the lecture, but
okay.
I'm probably gonna have to wait until the week.
Okay, sounds good. All right, it's 7 o'clock, so let's go and get started. All right, good evening, everyone. How's everyone doing today? Good, good, good. All right, and so today, today we're starting out with something important, and so I posted your final project, and so I did want to spend the first part of today talking about that, just so that we kind of go over all the requirements and just so that you know what you're going to be expected to do. Okay, and then after that, we're going to be going over, or excuse me, we're going to be continuing where we left off on Monday, which was learning how to implement 1D finite element codes. All right, and then if we have time, I do have another lecture notes here with me today, which is on 2D and 3D FEM, but we'll kind of see how far we get. Okay. All right, and so that's it for my announcements. So are there any questions I can answer before we get rolling today? Yep.
The MATLAB code, is it the finite element 1D starter?
Yes, yeah. So that's the code we're going to be working on. Mm-hmm. All right, and so let's go ahead and get rolling then. And so here is the final project. And so you might have noticed it. I'm actually not sure. It seems like Canvas notifies you whenever I publish an assignment, but just because I've gotten questions about assignments literally like 15 minutes after I posted it. But in case you weren't aware, if you go to the assignments tab there, then you can click on final project here, and you'll see all the files that you need for the final project. That we're going to talk about today. And so the one I'm going to be going over mostly is this one, which is the specifications. And so this is the kind of the description of the project about what you need to do for each part, as well as it gives you a little bit more background information on what you're going to do for them. Okay, so in essence, what you're going to be doing for your final project is you're going to be writing your own finite element code. Okay, so kind of building off our frame code, building off our truss code, building off the code that we're going to write today. Kind of the next step beyond that is to write your own 2D solver. Okay, and so what you're going to be doing is you're going to be solving the two-dimensional heat equation, okay, on an arbitrary mesh. And so this mesh here that you're seeing here is generated, arbitrarily, and so you're not going to know what the, where all the elements, you're going to know their shapes, and so they're all going to be triangles, but they're going to be arranged in kind of an arbitrary way. Okay? And you're going to write the code to solve the heat equation on this mesh. Okay, and so here's kind of a result. I think this is the end of I think this is the end of the entire project here. So after you've implemented all the parts, you're going to have a situation look like this. Okay, and so I chose this geometry just because I thought it'd be a little bit fun to do a geometry with curved edges, and so just so it's a bit different because up to this point you're going to be mostly working with straight edge situations. And so the fact that it's a curved edge right here, you get some kind of really interesting elements on the inside that you can that you're going to have to deal with. Okay. All right. And so I like this project a lot. I've kind of I'm piggybacking a little bit on some of the built-in structures within MATLAB. And so MATLAB actually has a toolbox inside called the PDE toolbox. And so with that toolbox, they have ways to produce kind of the finite element solution for you. Okay. And so that's really nice for us because then that gives you a way to kind of check your solution at each stage of the project, just to make sure that you're on the right track. Okay. Because I think the most difficult part of kind of writing your own code and kind of writing code from scratch is just kind of keeping track of, am I on the right track? Am I doing the right thing? And so to be able to have access to the correct solution kind of at all times, I think is a nice feature of this project, and it kind of helps you kind of check your work along the way. Okay, and so some of the terms I'm using in the specifications might not make sense at this point, and so that's what we're going to learn over the next couple of weeks. But a big part of this project is going to be to employ what's called the isoparametric element approach. Okay, and that's going to be a thing in 2D once we get there. Okay. And so this is a little bit of background information on isoparametric elements, and so I don't want to go over this yet just because we're going to be going over in the class. Okay, but the first thing you're going to need to do is you're going to need to install the PDE toolbox in MATLAB. All right, and so for if you just kind of have downloaded MATLAB to your computer and you've never used this before, it's probably likely that you don't have this installed. And so the nice thing is that if you're using if you're using the school license, it's available to you. The only thing is you just have to install it. Okay. And so here I have instructions how you can solve it. And so you click on the apps button. So I can show you here on this MATLAB here. Okay, so you go click on apps, and then you click on get more apps. Okay, and then it'll open up a page. Okay, and then you can search for PDE toolbox here. Okay. Oh, they have a CFD tool. That's interesting. Check that out sometime. Okay, and so if you search for PDE here, it'll be the first one here. So you're going to click on this. On this computer, it's already installed because we've installed a lot on these computers. But if you're running MATLAB on your home computer, you might not have it installed there. So I've included instructions here on how to download it, and then with that you can be ready to go. Okay? And so the equation that you're going to solve is this one right here. And so this is the 2D heat equation, right? And so we have K times the partial derivative of T with respect to X plus partial squared T partial Y squared plus the thermal generation function, which I have down here, is equal to 0. Okay, you're going to be using a constant K, and so you're going to be using a constant thermal conductivity. Okay, and you're going to be solving this equation. Okay, and so you're going to be implementing, a lot of different aspects of this code. And so in the end, it's quite a big code that you're going to be writing. And so I've broken it down into 3 different parts. Okay, and so the first part, what I want you to do is I want you to implement the solution to this problem using just simple diffusion. Okay. And so for this first part here, you're not going to have this thermal generation function, okay? And so you're just going to simply solve the 2D, basically the 2D diffusion equation on an arbitrary finite element mesh, okay? Okay, and so here kind of goes over some more details with respect to that, okay? And in fact, it might be actually good to look at the starter code. And so if you go to the project specifications, you can see here that I have starter code for each of the 3 parts. Okay, so let's go ahead and look at this one right here. Okay. All right. And so what you can see here is 3 variables here. So you have one variable that includes your thermal conductivity. So that's your K value. Okay. This next value here is probably the most important. So this determines the size of your elements, right? And so if you think back to when we did our ANSYS activities, you had to define what the size of your mesh was going to be, or in other words, how big your elements in your mesh are going to be. And so in this project, you have similar control, and so you can define how big your elements are, and then the mesh is going to compensate for that. Okay, and so if you decrease this number, you're going to have a mesh with more elements with a smaller size, but if you increase this number, you're going to have a more coarse mesh. Okay, and your code should be able to work across all different kinds of mesh sizes. Okay. All right. And so when you first run this code, you should see a figure pop up. And so the figure is going to show you, what your mesh looks like. And it's going to show you all the different ID numbers in the code as well. Okay. And so you're going to see a figure that looks like this. Okay. And so here you have, each of the edges on this domain here are going to be marked with an ID number. And that's going to be important for you to assign boundary conditions. Right. And so if you remember from the frame code, right? One thing that we did a lot in that code was we assigned boundary conditions to specific nodes in our mesh, right? And you're going to use that same logic here. And so if you look at the code, there's a section where you can define the boundary conditions in a very similar way that we did in the frame code, right? And so first you're going to specify an edge number, and then you're going to specify the value of the boundary condition that you want to apply there. Okay. And so in this particular case, we're going to apply a boundary condition of 100 degrees Celsius on edges 1 and 2. And so on this edge right here, okay, and this edge right here, these are both going to be held at 100 degrees C. And so that's your Dirichlet boundary condition. Okay. Edges 5 and 6, which are going to be these 2 down here, that's going to have a temperature boundary condition of 25 degrees C. And then 7 and 8, which are the top ones here, those are going to have a temperature boundary condition of 50 degrees C. Okay. The other ones, we're going to leave that alone because we're going to assign different boundary conditions to them later. But for this first part of the code, the idea with this first part is to just get the bare minimum to get a working code. And so you're going to implement the element stiffness matrices for a diffusion problem. Okay. And then you're going to implement the Dirichlet boundary conditions. And then after that, you should be able to get a working code, whose solution looks like. Well, it'll show you when you run the code. Okay. All right, and so here's a little bit extra on the data structures that I've defined for you. Okay. And in particular, in particular, I want to kind of talk about these two data structures right here, because this kind of comes straight from the MATLAB code. All right. And so the second data structure here should be familiar, right? And so if you remember from our frame code, we had this data structure called connectivity, right? And what that connectivity stated was for each element and for each structural element in your mesh, it told you which nodes were connected to that element, right? And at the time, you might have thought that this was kind of a strange way to implement that. But I did that on purpose because most finite element codes kind of use that same logic. And you'll see here that for this code, you're going to use that same logic as well. Because for each element in the mesh, right? For each element in this mesh right here, it's a little bit hard to see, but we have basically hundreds of triangles here. Each triangle is going to be connected to 3 different nodes, right? And each of those nodes are going to have an ID number. And so this might be node 10, right? This might be node 57. And this might be node 141, right? Okay. It's going to be a lot more random here because the mesh here is going to be generated, kind of at random, right? And so you need a data structure that keeps track of, which nodes are connected to which element, okay? And so you don't have to worry about populating this because this is going to be populated automatically. And so that's what we're kind of relying on MATLAB to do for us, and so you don't have to worry about forming these data structures, but you should know how to use them, okay? And so the idea with this is that, the idea with this project is that I want to build this off of all the other MATLAB codes we've worked on in the class. And so a lot of the similar aspects that you've seen in the truss code and the frame code and in the code that we're working on today, you're going to see a lot of those aspects in this final project code as well, both in terms of, the overall structure of the code, of course, but also in terms of the data structures that we use and how we actually use them to, form element stiffness matrices and things like that. Okay. So that's the connectivity matrix. And so the other vector that you're going to need to be aware of is the nodes vector. Okay. And so what the nodes vector is going to list out is that it's going to list out the X and Y coordinates or the physical locations for each node in your mesh. Okay. And that's going to be important in forming the element stiffness matrices later on. Okay. Right. And so if you kind of read the specifications here, then I have basically told you the size of each of these matrices. Okay. And you can verify this after you run the code as well. Right. And so take note about how big these matrices are and how to actually use the data in those matrices. Okay. All right, and then after that, you have kind of your normal stuff. And so you have a variable that stores a number of nodes, okay? And so you have a variable that stores a number of elements, okay? Then you have your global stiffness system, you have your global forcing vector, and you have your element stiffness matrices and element forcing vectors as well, okay? And so a lot of similar data structures that you've seen before, it's just that now they're kind of, they're kind of turned up a notch because you have a very large mesh with a lot of elements. Okay. But all of this is kind of written for you. And so again, you don't need to worry about forming these matrices. What you're going to need to worry about is how to use them in the code. Okay. All right. Any questions on this so far? Okay. All right. Let's see if there's anything else. Okay, and so when you write this part 1, so part 1 will probably be is probably going to be the most code that you're going to write because you have to write kind of everything here. And so you have to write code to compute the element stiffness matrices. You have to write code to assemble them. You have to write code to apply the boundary conditions, and then you're going to have to run them. Okay, but again, a lot of that logic is being already taken care of, or we've done them before in a lot of our previous codes. Okay, so I want you to kind of rely on all the codes that we've written up to this point and use them to help you with the final project. Okay? So part 1 is going to be worth the most points because that's the most functional part of the code. Right? It's not that parts 2 and 3 are still worth a significant amount, but part 1 kind of has the most moving parts. And so if you can get past part 1, that's already, I think, about 50% of the points of the project right there. Okay. Okay, part 2. So part 2, I want you to basically take your part 1 code and extend it a bit further. And so the way that you're going to extend it is you're going to add a thermal generation function. Okay. And so we'll be going over today about how to incorporate that into a code. But you're going to be basically doing this for a 2D function, okay? And the function that you're going to add is this one right here. And so that's going to be, what is that, 100,000? Yeah, it's about 100,000 times x squared times y squared, okay? And so the key here is that, you know, and we'll go over this today as well, is that when you apply this function, right? And if you remember from our lecture, you know, before spring break, whenever you have a function like this, you're going to have to end up integrating it. Okay. Right. You're going to have to integrate it together with the shape functions. And so the way that you're going to implement this is through Gauss quadrature. Okay. And so Gauss quadrature is something that we went over last time. And so you're just going to be applying in 2D. Okay. And so I don't think you need any Gauss quadrature for part A, because the thermal conductivity is constant. And so I don't think you need any of it there. But for part 2, you're going to need to use Gauss quadrature for that. Okay. Because otherwise you're not going to be able to evaluate this integral. Okay. Okay. So that's part 2. Part 3, you know, even though part 1 is going to be the most code that you're going to write, I think part 3 is going to be the most challenging code that you're going to write. So part 3 is to implement Neumann boundary conditions. Okay? And so if you remember, you know, when we're talking about heat transfer equation, when we're talking about Neumann boundary conditions, we're talking about heat flux of some kind. Okay. And so part 3, you're going to implement code to solve for the solution when we have this flux term. Okay. And so because we're in 2D, it's the logic for it is a little bit complicated. And so I kind of tried my best to kind of explain it here as much as possible. Okay. And so I'm not going to get too much into it here. You know, but we'll kind of circle back to this kind of later on in the class once we kind of get to this part. But this part will probably be the most challenging. And the last time I ran this project, this was the part that kind of tripped people up the most. Okay. I think for the most part, people were able to do part 1 and part 2. You know, of course, you know, people had questions on it, but part 3 is the part that really kind of tripped people up. And so I kind of modified the points a little bit because, you know, ultimately what I want you guys to get from this is part 1 and part 2. I think that's the most important parts. And so part 3 is kind of, you know, it's a required part, but I've kind of lowered the point total. So I think this is only worth maybe like 15, 20% of the total points of the project. Okay. Okay. And so the main difficulty with this is that, you know, because you have arbitrary elements here, you need a way to kind of find out which edge on your element is actually on the boundary, and that can be a little bit tricky, you know, just kind of based on the structure of the code. Okay. Okay. And so those are all the required parts. And so part 1, part 2, part 3 are all required. I do have an opportunity for extra credit here. Okay. And so if you want, you know, this is bonus, so it's not required at all. You can take the code that you've written in part 3 and improve its efficiency. Okay. And so what do I mean by that? And so right now, the way that the code is structured, it's structured in a way that's, I would say, optimized for learning. And so, you know, and so I know for a lot of you, this will be your first time writing a code of this size, a code that's you know, solving a finite element situation. And so it's not really designed to be a good working code for practical use. Okay. And so for bonus here, what you can do is you can take your code and then improve its efficiency. And so there's lots of ways that you can do this. And so you can make it so that it runs faster. Okay. You can make it so that it's a lot more memory efficient. Right. And so because the way that I've structured the codes, and this is true for the truss code and the frame code too, it's very inefficient in terms of memory. It stores way too much data that it needs to actually solve the problem. And so you can kind of fix that problem there. Okay. Or, you know, if you want, you know, if you can think of a way to improve the code that I haven't mentioned here, then go for that as well. Okay. There's probably lots of different ways that you can improve this code. And so, you know, if you find a good way to improve this code and you kind of detail that in your report, then that's going to be worth extra credit. Okay. Okay. And so just to kind of summarize all the different parts of the code that you're going to write, here are all of them. Okay. And so you're going to write up, you know, the data structure to help you with the Gauss quadrature. You're going to compute the element stiffness matrices, compute the element forcing vectors. Right. You're going to assemble the linear system, apply the Dirichlet boundary conditions, apply the Neumann boundary conditions, and if you want, you can improve the efficiency of the code. All right. Any questions on this? Okay, so deliverables. And so, you know, I've kind of, you know, it's a lot of code to write, but, you know, in the end, what you're going to submit is you're going to submit your code, but you're also going to write a final report on it as well. And so, you know, because it's a lot of code to write, I've kind of summarized here all the figures that you're going to need. Okay? And so first of all, you're going to need to display your results at the end of each part. Okay, so that you're going to display the results in part 1, part 2, and part 3. Okay. And so I say I want you to compare here because I want you to compare it to the true solution, right? And so I've written the starter codes in a way that it'll show you, you know, based on MATLAB's tools, you know, what the true solution should look like. And so ideally, the solution that you produce and the solution that MATLAB produces, you know, those two should be identical. Okay. And so I want you to show that here, you know, in your final report. Okay. All right, another thing I want you to do is I want you to perform a mesh convergence test. And so once you have a working part of your code, once you have a working code, I want you to compute your solution at different mesh densities. Okay, and so you're going to start with the coarse mesh and then refine it. And then you're going to report your results here. Okay. Next, I want you to change the boundary conditions to some way. Okay. And so as you're writing the code, you know, the boundary conditions are going to be more or less fixed. Okay. But I want you to kind of change the boundary conditions so that you can see how that changes your results, right? And then if you choose to do the bonus part, I want you to kind of show me your results from that as well, okay? And so all of these plots will be part of your final report. And so what you're going to submit in the end is your final report and the MATLAB code from all three parts. Okay. All right, question. So do I let you send it? Am I? Yes. And so the question is, can you send me your codes to let you know if you're in the right direction? Absolutely, yes. And so please, and I would ask that you do that instead of, you know, spending your time, you know, banging your head against the desk. And so I'm here to help you guys. And so, you know, it is going to be a big code to write. It's going to be a lot of code to write. And so, you know, please reach out to help whenever you need it. Yeah. And I think with these codes, you know, it's the best way I think for me to help you is if you kind of send me your code, then I can kind of look at it at my desk kind of with a fine-tooth comb. And so that's kind of the easiest way for me to help you out with that. So so definitely, absolutely. I'm not going to write your code for you. And so you know, I want to make that clear. And so I'm not going to tell you to write this code here, write this code there, you know, but I will give you hints in the right direction if I see you kind of going in a wrong direction there. Question. So do I want to submit everything in a zip folder or copy MATLAB code in PDF? And so when you submit your final project, you should submit 4 files. And so you don't have to zip them up. You can just submit the 4 files individually. So you can submit the PDF and you could submit the 3 MATLAB codes, you know, all in the same assignment. Yeah. Okay. And so let's talk about the final report. And so I've included a template for the final report. And so if you go to the assignment page, you can download that Word document. Okay. And so the final report is basically going to be, it's going to be written in the style of like a technical report, and so, or a scientific journal paper, right? And so it's going to have an introduction, a methodology section, a results section, and a conclusion. Okay. I don't have a page limit, or I don't have a page requirement, and so you can write as much or as little as you need to. And so I think everyone kind of writes a little bit differently, and so I don't believe that, you know, I should place limitations on that. I get reports that are, you know, 30, 40 pages long, but I also get reports that are like 8 pages long. And actually, a lot of the times, the 8-page report scores a lot better than the 40-page report, just because they're a lot more efficient with what they say. Okay, but if you want kind of a ballpark estimate, you know, just kind of based on what I've seen in the past, maybe around 12 pages is kind of what the average is going to be. Okay. But again, that's not a requirement. So you're welcome to add more or less as you see fit. Okay. All right. And so this part's important. And so I you know, whenever you produce any kind of writing, you know, it's always important to keep in mind who your audience is going to be, because that's going to change, you know, how you write certain things, the level of detail that you use, and what terms you can use. Okay. And so your audience for this project is you can assume that it's going to be one of your peers. Okay. And so it's going to be a fellow graduate student in mechanical engineering. But you're going to assume that they have not taken this class. Okay. And so they might be aware of what finite elements is in general, but they don't know what things like element stiffness matrix mean. They don't know what a mesh is. They don't know what Gauss quadrature is. Okay. And so I want you to kind of write this report. Part of this report is I want you to kind of write it from the perspective of you trying to teach someone, what you've learned in this class, right? Because we've learned a lot in this class, and we're going to learn a lot more in the next few weeks. Okay? And so I want you to be able to show off, what the knowledge that you've learned. But you can expect some reasonable technical knowledge as well. Okay, so that's why I kind of say, write it as if you're kind of trying to teach someone of your level. Okay. Okay. And so with that said, here are the components of the final report. Most of it's pretty standard, but I want you to focus a lot on the methodology. Okay. And so just like I mentioned, you're kind of writing this report with the intent to teach someone. Okay. And so I really want you to dive into the methodology. And so, I want your methodology section to have equations, right? You don't have to do full-on proofs. You don't have to do full-on proofs like we do in the class, but you should be able to say, this is the equation for the element stiffness matrix, right? And so here's a description of how we obtain that element stiffness matrix. Okay. Here's a formula for what the shape functions look like, and here's an explanation for what shape functions mean and what they're used for. Okay. Here's a description of what assembly means, right? And here's kind of a little algorithm to show you what assembly is and why we need to do it. Okay. And so think about the class at kind of a high level and explain a lot of these topics, right? Explain a lot of, basically walk someone through your code. And so, explain someone, why you wrote this code in a certain way and what that means in terms of the theory. Okay. And so, this section is really important, and I think it's a really important section for a project like this, which is basically an end of term project. Okay? Because this is how I'm going to assess, how much you learned from the class. Because we're not going to have a final exam. The only final thing that we're going to have in this class is this one. And so, the way that you're going to demonstrate, basically your mastery of the material is one, that you're able to write all the codes that are required. And two, that you're able to kind of explain what you're doing. Okay. And that's kind of the purpose of this methodology section here. Okay. All right, so a couple final remarks. And so teams, there are no teams. And so this is an individual project. And so everyone's going to write their own code. Everyone's going to write their own report. But with that said, I do encourage you to work together with your classmates in developing the code. Okay. And so, literally every single person in this class is going to run into a snag in the code at some point. If you don't, then you're a coding savant, and I'm gonna ask you to teach me how to code as well. Okay. And so, your best source of knowledge, one of your best sources of knowledge in this class is actually going to be from your classmates, because, if you're running into a certain issue with your code, chances are someone else is going to be running into that same issue. Okay. But also what could happen is someone else might have ran into that issue and they might have gotten past it already. And so, use that Discord server, talk to the friends that you have in the class and work together to kind of develop the code. I think that's a great learning opportunity. Okay. But I want to be clear, when I say work together on your code, that does not mean that one person writes the code and everyone else copies it from it. Okay. That's different. And so, struggling through the code and kind of writing it yourself, that's kind of part of the learning process. And I want everyone to kind of go through that for this project. And so if you kind of copy the code from someone else, first of all, it's super obvious if you do. And second of all, you're kind of robbing yourself of a big learning opportunity. So please, work. So you can absolutely work together with your friends, absolutely work together with your peers in the class, but just kind of make sure that you're writing the code yourself and you're kind of understanding everything that you're doing. Okay. Okay, and so final remarks. It's a lot to do. It's not a small project by any means. It's a lot of coding to do. It's a lot of writing to do. And so, please don't hesitate to reach out to me. Okay, so I'm here to help you, as with anything in the class, and and this project is no exception. Okay, and so if you're struggling with the code, or if you not sure how to proceed, or if you're getting an error in your code, or you're not sure how to write your report, that's what I'm here for. It's my job. It's just my job to kind of help you through those things. So please, reach out to me, and I promise you I'll do everything I can, and I'll get back to you as fast as I can to help you out with this. Okay. All right. Oh, and I forgot. Due date. I know I mentioned it briefly on Monday, but this project is going to be due on Monday, May 23rd. And so you have about a month and a half to finish the project. Okay. And so if just like I mentioned on Monday, so finals week is actually the week before this. and this is the day of graduation, actually. So, you know, I like to kind of push my final project due dates to be back as far as I can, just because, you know, I know you guys are going to be probably busy during finals week, and some of you might be busy for graduation. And so I want to kind of push that back so you have that extra weekend to work on this if you need to. Okay. But I can't really push it back any further than this because I need to finish grading by the end of this week. And so I need to submit final grades, I think, by May 30th. And so that's as late as I can push it because I have 3 other classes that I need to grade stuff for as well. Okay. All right, any final questions on the project? Yeah. It's not so bad. It's not so bad in the summer. Fall semester is worse because it's before Christmas. And so I'm like grading, but also trying to buy presents for my friends and family at the same time too. So this is a little bit better. Oh yeah, of course. You're also welcome to turn in early too, and so you know you don't have to wait till that date. And so if you turn in early, then I can actually grade it early, and that helps me too. But yeah, I know how hectic. You know, it hasn't been that long ago that I was a student. I'm still young. God damn it. And so I remember, you know, I still remember what it's like. And so you know, I know that little bit of extra flexibility I know can go a long way. And so you know, I'm happy to provide as much of it as I can. Okay, and so that's the final project. And so, you know, I posted the rubric here, and so you can look and see how the points are broken down. You know, I'm not going to go through it here, but you can see, you know, how the results break down for each of the different sections. Okay, and so let's go ahead and pick up where we left off on Monday. And so on Monday, we were going over these set of lecture notes. And so this is basically a lecture on how we can implement our 1D finite element problems. Okay. Using the method that we've gone over recently. And so all of the you know, integration by parts, element stiffness matrices, right? So this is kind of the more general finite elements. And so this is going to be our first foray into implementing this in MATLAB. Okay. And so you're going to see, you know, a lot of the concepts that are required for the final project are going to be here, right? Especially, I think the part that's going to be most useful here is the Gauss quadrature integration. And so I want to make sure I go over that, you know, very carefully, because you're going to be using that for the final project. Okay. All right, and so let's go ahead and open up the code. And so, you know, this is the code that I've written from Monday. And so, you know, if you compare that to what's posted online, I think I filled in a lot of this kind of introductory information here. And so I've implemented the size of the domain, the thermal conductivity, the cross-sectional area, the Dirichlet boundary condition, the Neumann boundary condition, the number of elements, and, you know, the coordinates and the size of the elements. Okay, and so we can go ahead and run through that in the presentation here. So let me see if there's a better way to do this. View. No, reading view. There we go. Okay, that's a bit better. Okay. All right, so here's the problem, just as a reminder of what we're going to solve. And so we have basically a rod that's fixed to a wall, right? And so the wall is going to be a fixed temperature. And so the rod is going to be, or the Dirichlet boundary condition on the left side is going to be 25 degrees C. Okay. The length of the rod is 5 meters. We have a Neumann boundary condition on the other side, which is a heat flux of 600 watts per meter square. Our thermal conductivity, K, is a constant here. It's 50 watts per meter degree C. We have a constant area, so the area is 0.1 meter square. And we have thermal generation here of x squared. Okay. And so for this problem, you know, we have an exact solution. And so we have a solution that we can refer to. And so that, again, this is similar to the final project. And so when we finish developing our code, we can compare what our solution looks like compared to the exact solution. Okay. And so for the first part of this code, you know, we did this on Monday. We went ahead and filled in all of these parts. And so if you're downloading the code from the starter code from online right now, you might see that these parts are not filled in. And so all I did for this first section here was I took the parameters from the problem and filled them into the appropriate sections here in this part. Okay, so I filled in the length, thermal conductivity, area, T naught, Q naught, and the number of elements. Okay. And again, you know, we're writing this code, you know, we're writing this code to be as generic as possible. And so, I want to write this code so that if I change the number of elements from 5 to 50, then the code is automatically going to update based on that. Okay. All right. And so, we talked about this on Monday. And so one thing you'll notice that there's no connectivity matrix, because the connectivity information for this problem is pretty trivial, because we have just a 1D line. Okay. And so for any given element I, its left node is going to be I, and its right node is going to be I plus 1. Okay, so here are the data containers. And so here are the data containers for K global, F global, K element, F element. Okay, so that's the global stiffness matrix, global forcing vector, element stiffness matrix, and element forcing vector. Okay. All right, so next we have the nodal coordinate vector. And so we did this last time as well. And so one thing that we're going to need when we run this code is that we're going to need to know what all of the endpoints are going to be located. Okay, and so we use the function linspace for that. And we also have to learn what we also have to know how big each element is. And so that's going to be L element. Okay. And we fill that in the code right here. And so we use the linspace function, and we use linspace from 0 to L, and the number of entries that we need is number of elements plus 1, because the number of nodes that we have is 1 more than the number of elements, and the length of each element is just the total length divided by the number of elements. Okay. Okay. And so the next part of the code is the element stiffness matrix. Okay. So this is the part when we are going to start to really develop this code. Okay. Let me go and close it. All right, and so if you recall from our lectures, our expression for the element stiffness matrix is the following, right? And so we have our two shape function derivatives here. So we have dn1 dx, dn2 dx multiplied by k times a times dn1 dx, dn2 dx. Okay, integral from the left side of the domain of the element to the right side of the element. Okay, all of dx. And so if you remember the really long example that we did before spring break, we basically worked through this for two problems. All right, and so we're going to write the code here to kind of solve this expression right here. Okay, and so the first thing we're going to do is we're going to write out the expressions for the two shape function derivatives. And so if you remember, unfortunately I don't have it here. And so you remember the expressions for n1 of x. Remember, n1 of x, the shape function, is equal to x minus x2 divided by x1 minus x2. Okay. That was our linear shape function for our 1D element. And so if we take the derivative of this, we take dn1 dx, right? This x2 term is going to go away, and all we're left with is 1 divided by x1 minus x2, right? But the way I get LLM here is I take note that if we take x2 minus x1, right? And so in other words, I take the difference between the x coordinate of the right node minus the x coordinate of the left node. All I get here is the length of the element, right? And so that's basically the distance that would travel from the left to the right, okay? And so if x2 minus x1 is LM, then 1 over x1 minus x2, this is the same thing as negative 1 over LE. Okay? And so that's how I get this formula here. And then by similar logic, if you write out the equation for n2 of x and you take its derivative, you're going to get 1 over LE. Okay. Okay. And so let's go ahead and implement that in the code, because we know what the length of the element is, right? And so the length of the element here is LLM, right? And so let's write out the expression for dn1 dx, right? And so I've written kind of the skeleton code for you here. And so from the PowerPoint here, we can see that dn1 dx is going to be minus 1 divided by the length of each element. And if we assume that each element is the same size, then that's all we have to do for this code. Right? So we do -1 divided by 1 divided by L element. Okay. And then you can use that same logic to write out the expression for dn2 dx, right? So dn2 dx is going to be 1 over LE. Okay. And so, of course, if we implement that in code, that's going to be 1 divided by L. Okay. And that's going to be valid for every single element, right? And so this is the benefit of using linear shape functions, because when you use linear shape functions, then the shape function derivatives here are just a constant. And so you don't have to worry about how things vary element by element, because they're all going to be the same. Okay. And one thing I kind of skipped over before we got to this point is we obviously have a for loop here. Okay. And if you remember from the truss code and the frame code, right, we had a very similar structure to our code in that we used this for loop. Right, this for loop is used to visit every single element in our mesh. Okay. And so for each element, the way that you can interpret this loop is that we're going to be visiting each element and forming its element stiffness matrix. Right, and that starts by computing the shape function derivatives. And so the first thing we're going to compute is dn1 dx. dn2 dx, and we're going to use that to compute the element stiffness matrix. Okay. All right, any questions on this so far? Okay. Okay, so let's go back to the code. And so the next thing we're going to write here is the code for the call vec and the row vec. Okay. And what those refer to these two vectors right here, right? And so here we have a dn1 dx, dn2 dx, and they're arranged in a column vector. Okay, so this is call vec. Okay. And on the right here, we have dn1 dx, dn2 dx, but this is arranged as a row vector. Okay. Okay. And when we multiply the two together, right, that's what gives us our 2 by 2 element stiffness matrix, right? Because in the end, when we finish this operation, we should get a matrix that's 2 by 2. Okay, and so if this column vector here is 2 by 1, right, and then we multiply by a row vector which is 1 by 2. Okay, these two inner dimensions are going to cancel out, and we end up with a vector that's 2 by 2. Okay, and so to obtain that, one way that we can do that is we can form this column vector and we can form this row vector. Okay, and all they're comprised of is just the shape function derivatives. And so let's go ahead and fill that in. Right, and so the column vec, you can see here we're going to have dn1 semicolon dn2. Okay, and the fact that we use a semicolon means that we're going to have this is going to be a 2 by 1 column vector, right? Because we use a semicolon here. The row vec, on the other hand, will have the same entries on the inside. So we have dn1, dn2. Okay, but instead of a semicolon, we're going to have a comma. Right? And so the resulting size of this vector is going to be 2 by 1, right? So it's going to be 2 rows because it's a column vector and only 1 column. And the size of this one is 1 by 2 because we just have a single row, but we have 2 columns in that row. Okay. So now that we have call vec and row vec, all we have to do is just multiply these together in order to form KE. Okay, and so we can take advantage of the fact that MATLAB does vector and matrix multiplication super well. And so if we do call vec multiplied by row vec, okay, this is going to produce our 2 by 2 matrix, right? Because we're multiplying a 2 by 1 column vector and a 1 by 2 row vector, and so that's going to give us a 2 by 2 in the end. Okay. So this feature is really nice, and so there's not that many codes that do matrix multiplication like this really well. So this is a really nice feature of MATLAB. Okay. Okay. Any questions on this? Okay. All right. And so let's go back to the code here. Okay. All right, and so we've multiplied these two. And the nice thing about this is that when because dn1 dx and dn2 dx, both of these are constants. And so when we multiply them together, the whole thing just becomes a constant. And so the whole thing kind of just gets, moved outside of the integral. Okay. And that's exactly what we have here. Okay. And so, after we perform dn1 dx times dn2 dx, all of that is a constant, so we can move it out of the integral. And all we have left is just integral from x1 to x2 of k times a. Okay. Okay. And so another nice thing here is that both k and a, these are also constants. And so because these are constants in this case, we can kind of pull these two out. Okay. And then the result is that, we just end up multiplying our entire matrix by k and a. Okay. And I didn't write it here. And in fact, I kind of messed up in the tooltip here. Okay. And so after that, what you're going to get is k times a times your 2 by 2 matrix. Okay. And you're going to multiply that by integral from x1 to x2 dx. Okay. And so you still have an integral that you have to do here. And so if you integrate this, you have integral of 1. And so you're going to have from this integral right here, you're going to have x2 minus x1, right? And we know what x2 minus x1 is. x2 minus x1 is just the length of the element, right? Okay. And so what you should be multiplying here is not just k times a, but you should also multiply by LE as well. Okay. All right, and so basically we're going to take our result from the previous line of code and then multiply it by the thermal conductivity, by the cross-sectional area, but also by the length of the element as well. Okay, so let's go ahead and do that. Okay, so that's what this line of code here is. Okay, so we're going to multiply by. And so we're going to take our result from up there. And so we're going to take k times e, or k underscore e. So that's our 2 by 2 vector. So we're going to multiply by k. We're going to multiply by a. And we're going to multiply by ln. And so that's going to be our element stiffness matrix, right? And so that's it. And so there's not much more to it. And so the nice thing about this and using linear elements is that everything is a constant. And so you don't really have to integrate anything. And so you end up just multiplying by a bunch of constants. Okay. And so the last step here is we need to save this to our data structure. Okay. And so I'm gonna go ahead and write this in for you because I believe I wrote this for you for the truss code as well. Okay. Okay. And so what we say is that the element stiffness matrix for this element is equal to KE, which is what we just computed. And so all this does is says that, for this particular element, we've already computed the element stiffness matrix. And so we're basically storing that in our data structure. Okay. All right. Any questions on this? Okay. All right. So this part is because it's a 1D problem, it's a lot smoother. It's a lot easier than our truss and frame code. And so, that's kind of the nice thing with using linear shape functions. Okay. All right. So next we enter what I consider kind of the most new parts of this code, which is the element forcing vector. Okay. So let's kind of come back to the presentation here. Okay. And so if you remember, before the spring break, we had our element forcing vector and it had the following expression. And so we had integral from x1 to x2 of our two shape functions, n1 and n2, multiplied by our thermal generation function plus our Neumann boundary condition. So this contribution here is from the Neumann boundary condition. Okay. And this contribution here, because it has the s of x, this comes from our thermal generation. Okay. Okay, and so we're going to focus on this first, and so we're going to focus on the generation term because the way that we're going to accomplish this integral is through Gauss quadrature. Okay, so that's what we talked about on Monday. Okay, and so if we plug in for each of the shape functions, and so the shape function n1 is x2 minus x divided by LE, n2 is x minus x1 divided by LE, and we plug in for s squared, or s, which is just x squared. Okay. If we distribute this x squared through this vector right here, then we get x squared x2 minus x cubed, and we have x cubed minus x1 x squared. Okay. And so this integral here it's not the hardest to compute, but this is a good opportunity to kind of apply what we learned on Monday, which is the Gauss quadrature integration. Okay. And so in other words, we want to compute this integral without actually computing the integral. Okay, so we're going to evaluate this numerically. And we're going to do it with a two-point Gauss rule. Okay. Right, and so that's what the code that we're going to write here is for that. Okay. And so let's take it kind of step by step. Okay. And so the first thing is to input the Gauss points for the two-point rule. Right? And so if you look back in your lecture notes from before the spring break, you know that for a two-point Gauss rule, and so we're integrating from -1 to 1. Okay, we're integrating from -1 to 1 of some function f of x, okay, dx. Right? Then we know that if we use a two-point rule, then the psi1 or the epsilon1 is going to be -1 over √3. Right? And so that's the first location where we're going to evaluate our integran. And our second location where we're going to evaluate our integran, epsilon2, is a +1 over √3. Okay. And so this first part of the code here, I want you to kind of write this down. So I want you to establish, where the Gauss points are that you're going to use for this integration. Okay. Okay, so we have GP1, and so GP1 here. And GP1 here is just simply going to be epsilon1. So this is going to be -1 divided by square root of 3. Okay. And then GP2 is going to be 1 divided by square root of 3. Okay. Right, and so that tells the code, or we basically established that we're going to use the two-point Gauss rule, and these are the Gauss locations that we're going to use for that. Okay. Okay. Any questions on this so far? Okay, let me go ahead and clear this. Okay, so the next thing that we're going to do is we need to obtain the nodal coordinates for this element. Okay, and so once again, I kind of glossed over this again, but you can see that we're looping over each of the elements. Okay, and so if we have here's our domain, right? And so let's say that we're considering this element right here. Right? And so in order to properly perform this integration, we need to know what the coordinates are for this element, for this node, okay, which is the left node, and this node, which is the right node. Okay. And so we'll call this x1 and x2. All right. So luckily for us, we've already have this defined, and so we've already defined this from the beginning as pos vector, right? And so let's use that pos vector here to compute what x1 and x2 are. Okay. And so x1, so that's the location of the node on the left of the element, and so we're going to do pos vector at IE. Okay. And then x2 is going to be pos vector at IE plus 1. Because remember, from the slides before, okay, if we have a certain element I, in this case we do, and so because we're looping over the elements, okay, the leftmost node is going to be, or the left node of that element is going to have an index of I, so the same as the element, okay, and the right node is going to be I plus 1, right? And so we use that information together with the pos vector, variable here to compute or to reference, what the physical coordinates are for each of those nodes. Okay. Any questions on that? Okay. All right, so now that we know the Gauss points, now that we know the physical coordinates, the next thing is to compute what the x coordinate is at those Gauss points. Okay. And so in other words, we're going to compute x of epsilon, right? So remember that was kind of a key component of our Gauss quadrature from Monday. Okay. Okay. And so if you remember from Monday, you know, we used these kind of specialized shape functions, right? And so, you know, assuming our domain is from -1 to 1, then our shape functions in terms of the Gauss coordinate is 1/2, 1 minus epsilon, and then the second one, n2, is 1/2 times 1 plus epsilon. Okay. And so we can compute, you know, what x of epsilon is at both of these locations, right? And so the way we do that is we take x1, x2, x2 being the physical coordinates of the node. Okay, we multiply them by the corresponding you know, shape functions, but we evaluate these shape functions at the Gauss points. Okay, and so you can see here I have x of epsilon 1. Then I take the shape functions here. Okay, and so I take this function. Okay, but for epsilon, I'm going to plug in -1/√3. Okay, and so in other words, we're basically evaluating this this coordinate function at the two Gauss points in our element. Okay, and same thing here. And so whenever you have an epsilon 1, that's going to be -1/√3, because that's the Gauss point at that location. Okay, and so same thing here. And so same thing, you know, but for the second one, we're going to plug in epsilon 2. And so epsilon 2, we're going to have a 1/√3 and a 1/√3. Okay. All right, so let's go ahead and write the code for this. And so let's start with x of epsilon 1. Okay. All right, so x of epsilon 1, so I'll call this xgp1, will be x1 times n1 at gp1 plus x2 multiplied by n2 of gp2. Okay. All right. So that's the concept, right? And so all I did here was I basically just copied over this formula, right? So x at epsilon 1, so xgp1 is x1 times n1 at epsilon 1 times and x2 times n2 at, oh, this should also be gp1. Okay, but we don't have these functions here. And so we need to kind of wire this in by hand. And so, you know, n1 of gp1, we're going to go ahead and plug in our function here. And so n1 is 1/2, and so we can do 0.5 multiplied by 1 minus gp1. Okay. And so this quantity right here, this quantity that I just wrote, this is n1 at gp1. Okay. All right, so let's do the same thing for n2. So n2 is 0.5 times 1 plus gp1. Okay. And so again, this quantity right here, this is n2 at gp. This part is a little bit confusing to get, but you know, basically, you know, if you remember from Monday, you know, we had to compute, you know, what these shape functions are we need to compute what this coordinate function is at each of the Gauss points so that we can kind of plug it into our Gauss quadrature later. Okay, and so that's basically kind of what we're doing at this point. And so while I'm here, let me go fill in the bottom one here. And so the bottom one here is going to be a carbon copy of the top one here, except we're evaluating it not at GP1, we're evaluating everything at GP2. Okay. So I'm going to switch those to GP2. Okay. All right. And so, you know, I think this might be a little bit different from how we did it on Monday. And so we're kind of doing things a little bit out of order. You know, because I think first thing we did on Mondays was we formed the function x of epsilon, right? And so it was a general function that was based on epsilon. Okay. Okay. And so I think that's the first thing that we did. And then in the example we did, we took this x of epsilon and we plugged it into the integral to perform our change of coordinates, right? Right. And so if you look back into the example we did on Monday, that's basically what we did. We had an integral, and everywhere that we saw x, we plugged in for x using this function. And so we effectively changed the coordinate. Instead of integrating over x, we're integrating over epsilon instead. Okay. And then once we plugged it, and then once we plugged that into the integral, that's when we evaluated it at the different Gauss points. Okay. So now we're just kind of doing this a little bit out of order. And so we form this function here. And what we say is that, okay, eventually we're going to need to evaluate this at our 2 Gauss points because we're doing a 2-point Gauss rule. And so let me just do that first here. Okay. And so I kind of did those 2 steps together. So I formed this x of epsilon coordinate function, and then I evaluated them at the Gauss points because that's what we're going to need, in the next step to perform the Gauss quadrature. Okay. All right. Any questions on this step here? Okay. All right. So now that we have xgp1, xgp2, the next step we need before we perform the integral is to form the Jacobian. Okay. And so the Jacobian, remember, is just the derivative of our coordinate function. And so we have x of epsilon, which was on the previous page. Well, I just erased it. Okay. And so if we take the derivative of that with respect to epsilon, we get x1 times dn1 d epsilon plus x2 times dn2 d epsilon. Okay. But we actually evaluated this on Monday. And so when we evaluated this, then we got that dn1 d epsilon, this is just a -1/2. This dn2 d epsilon, this is a positive 1/2. And so we end up with just x2 minus x1 divided by 2. Right? That was the value of the Jacobian for our 1D case. And so let's go ahead and plug that in here. And so we have an x2 minus x1. We've already defined those because we have them here in the function here, or in the loop, and then we're going to divide that by 2. Okay. Our question: so you could you use LLM? Yeah, absolutely. And so LLM is actually the exact same. And so since every element here is equal, instead of doing x2 minus x1, you can do L. And so that'll give you the same thing. Yeah. Mm-hmm. Yeah. That's a bit more true to how we interpret the Jacobian from before. Remember, the Jacobian is a scaling factor that scales for the fact that we're changing kind of the size of the integration domain. Okay. So that's the Jacobian, and so that's fairly easy. And so now we actually have to evaluate our integral here. And so this is where things get a little bit interesting. Okay. And so if we go back here, right, the integrals that we're actually evaluating are these ones right here. Okay. And remember, the point of Gauss quadrature is that we're not going to take the antiderivative of this, but we're just going to evaluate this integrand. Okay. We're going to evaluate this integrand at the Gauss points. Okay. And so let me go ahead and just do this first one up here, just so that you kind of see what it looks like. Okay. And so basically everywhere that we see x, we're going to replace it with our x of epsilon function. Okay. And so let me do that for xgp1 first. Okay. All right. So we can see here that we have. Let me go ahead and write it up here. So we have an x squared times x2 minus x cubed. Okay. So that's the integral that we want to evaluate. And out here we have a 1 divided by LLM. Okay. And on the right here, we're going to have a Jacobian as well. Okay. So that's the integral that we want to evaluate. So let's go ahead and implement that in the code. Okay. And so that's going to be this first one here. And so let me pull the constants out in front first. And so first we have Jack for Jacobian. Then we have LLM. Right? And so those are the constants there. And we're going to multiply by this function here, evaluate it at the Gauss points. So let me do the first Gauss point first. And so the first Gauss point is going to be x squared And so remember, instead of x, what we're going to plug in here is xgp. In this case, we're going to do xgp1 first. Okay. And so we're going to plug in this exact function right here, but for every time we see x, we're going to plug in xgp1. Okay. And so we have xgp1 squared, okay, multiplied by x2, and so that x2 is there, minus xgp1 cubed. Okay. All right, so that's the first part. That's the first part of the Gauss quadrature. But remember, we're doing a 2-point rule, and so we have to add this exact same thing. But instead of evaluating everything at xgp1, we're going to evaluate it at xgp2 instead. Okay, so I'm going to repeat the same thing. So let me add a plus sign here. Okay, so we're going to do the exact same thing here. But instead of xgp1, I'm going to replace this with xgp2. Right, so here's the Gauss quadrature, and so instead of integrating this, and so if we integrated this, this would be like x cubed divided by 3, x2 minus x to the 4th divided by 4. Right. So here it's kind of trivial. You know, we could have done this just fine. You know, but I wanted to illustrate how to do this with Gauss quadrature. Okay. Right, and so once you have the xgp's, and so once you have basically the x variable evaluated at the Gauss points, then all it is just plugging in for that into your integral function. Okay. Any questions on that? Okay. All right, so let me go ahead and delete this. And so now let's evaluate the second integral, which is on the bottom. Okay, so the second integral is going to be x cubed minus x1 x squared. Okay, so you have 1 divided by LE times x cubed minus x1 x squared. Okay, and we have a Jacobian out here as well. Okay. Okay, so let's return back to the MATLAB code. And so let me go ahead and multiply this by the Jacobian divided by LLM. Okay. And then we're going to evaluate this integral now. And so instead of x cubed, we're going to have xgp1 cubed. And instead of x squared here, we're going to have xgp1 squared. Okay. All right. And so we have xgp1 cubed minus x1 times xgp1 squared. Okay. And just like I did up there, we're going to repeat the exact same thing, but we're going to evaluate everything at xgp2. Let me copy this, plus, paste, and so this is going to be xgp2. Okay, and so those are our two Gauss quadrature functions. Let me just skip ahead here in the integral. Okay. All right. So I think that was probably the most difficult part of this code. Okay, and so to make sure you do the Gauss quadrature, and make sure you understand this, because Gauss quadrature is a big part of the final project as well. And for the homework assignment, your grade's going to repeat the element stiffness matrix, but you're going to do it with Gauss quadrature instead. Okay, and so that takes care of the thermal generation function. And so the last thing we have to do here is we have to add the Neumann boundary condition. Okay, and so the Neumann boundary condition only occurs when we're on the right edge. Okay, so if we go back to the problem statement, okay, the Neumann boundary condition is on the rightmost side of the domain right here. Okay, and so that only occurs when we're on the rightmost element here. Okay, right. And so if you go back to the weak form of the problem, you remember that there is a part of the equation that accounts for that Neumann boundary condition. But remember, we only make it active when we're on that Neumann edge. Okay, and so the only time we're going to add the Neumann boundary condition is when we're on the very, very end. Okay. Okay, so let's go back to the code. And so you can see here, I have an if statement that checks for that. And so what we say is that if the element index here, i.e., if that's equal to the end, right? And we know that we're at the end when i.e. is equal to n lm, right? And so basically, when we're looking at the very last element, the rightmost element, that's when we apply the Neumann boundary condition. Okay. Okay. And so the way that we're going to do this is that we're going to say that, you know, come back here. Okay. Our Neumann contribution is going to be this. And so we're going to take A and we're going to multiply by Q out. Okay. And then we need to evaluate the shape functions at x2 because the Neumann boundary condition only occurs on the right side of the element, right? Because here is our element. This is x1, x2, right? And let's assume that this is the very last element. And so the heat flux is occurring here, okay? And so the only place that we're going to evaluate this is at x2. And so we're going to take x2 and plug it in to our shape functions here, okay? And so we have n1 of x2, right? And so we take, we plug in x2 for that. We get x2 minus x2 divided by x1 minus x2. Okay, and so n1 of x2 is going to equal to 0 because we have x2 minus x2 up top. Okay, but if we plug in x2 into n2, we get x1 minus x2 divided by x1 minus x2. Okay, and this is going to equal to 1. Okay, and so the vector that we actually add is just this one right here. So we have a 0 up top and a 1 on the bottom. Okay. And so the way that we can implement this is that, you know, because we have a 0 up top, we don't have to worry about that. And so we're going to say that we're only going to do this in slot 2. Okay. And this is going to be equal to, we're going to add area multiplied by Q out. I think it was Q out, right? Q underscore out. Right, and so that takes care of our Neumann. That takes care of our Neumann boundary condition, because we're only applying that on the very right side of the domain. Okay. Any questions on the Neumann boundary condition? Okay. All right. So we have 2 parts of the code left, and we have 3 minutes, and so I think we'll probably finish most of it on Monday. Let's talk about assembly on Monday. And so, we've already talked about assembly before. This one is not going to be nearly as complicated, but I do want to talk about it again. And so let's talk about how we apply the Dirichlet boundary condition. Okay. And so the Dirichlet boundary condition, this is being applied on node 1. Right. And so remember the way that we apply Dirichlet boundary conditions is that we zero out the entire row. And so we're going to zero out the first row and place 1 on the diagonal. Okay. And so for this case, this is going to be the first row of the K global. Okay. And so this is going to be zeros. Yep. It is heat. Yep. We put the temperature on the right-hand side vector. And so what we're doing first is we're taking the element stiffness matrix and we're zeroing out that row of the element stiffness matrix. And so we're making this basically 1, 0, 0, 0.
Oh, I see. Okay. The temperature goes over there.
Yeah, temperature goes over here. Yeah. T naught. All right. So first thing we have to do is we have to zero out that row because after the assembly, there's going to be some stuff in here. Okay. There's going to be zeros, 1 row, and n lm plus 1. Okay, because that's how many nodes we have in the grid. And then we need to make the diagonal entry 0. So that's 1, 1. Or excuse me, we need to make the diagonal entry 1. Okay. And so K global at 1, 1 is equal to 1. And then we need to make, and so this is what's different about heat transfer. So instead of putting a 0 here on the right, we're going to make the 0 there. We're going to make the right-hand side equal to T naught, which is the prescribed temperature. And so that applies the Dirichlet boundary condition. Okay, and so the last thing we have to do here is we have to implement assembly, and so you can see here it's a lot shorter, and so we only have a 2x2 element stiffness matrix, but we are just about out of time, and so I don't want to keep you guys too long today, right? And so on Monday we'll finish this up. We'll finish up the assembly, and then we'll see what this looks like in terms of the solution. Okay. But again, the part I want you guys to focus on the most is this loop right here, which is the Gauss quadrature. So I think that's the most new thing that we're doing here, because a lot of the other things that we're doing in this code is kind of like a simplified version of what we've already done with the frame code and the truss code. So I think you guys kind of understand that, based on kind of what I've looked at from your previous ANSYS activity. And so for this code, I want you to focus on how we did the Gauss quadrature. All right, any final questions before we wrap it up for the week? Okay, all right, so thank you guys for coming today. Hope you guys enjoy the rest of your evening. Hope you guys enjoy your weekend. Let me know if you have any questions on anything. If you want to get started on the final project, I would definitely, start looking at it. And then just let me know if you have any questions. So have a great weekend, everyone. Thanks for tuning in, and I will see you on Monday. Yeah, for sure, for sure. Yeah, we did that kind of fast. And so for the Neumann boundary, I think probably the best place to start would be probably right here. Oops. Yeah. And so, if we go back to the basically the finite element form of the equation, then this is our expression for the element force expression. Right? So we have one expression here. This is for the thermal generation function, and then another part here for the Neumann boundary. And so, but this term right here, most of the time we ignore it. The only time when we don't ignore it is when we're at the Neumann boundary. And so that's why we only apply it at the very last element. Exactly. And so I think the thing that's a little bit tricky is that even when you're on that last element, right, you have this expression right here. So n1 of x and n2 of x multiplied by 8 times q. But you're evaluating this at the x where the Neumann boundary is. And so for this case, that could be x2. So that's the right hand side of it.
Oh, okay.
And so basically everywhere, exactly. Basically everywhere you see x, you're going to plug in x. For the a, doesn't make a difference here because our a is constant. And so this is just regular a. But when you plug in x2 into here, you get n1 is equal to 0 and n2 is equal to 1. And so that's why we have 0 and 1. And so the way we implemented that in the code, and so we had basically a vector like this 0, 1. I said, all right, since the first entry is going to be 0, I'm not going to worry about that one. And so I'm only going to plug in for the second entry. And so for the code, that's why here I have f element at 2 is equal to f element 2 plus this. So I only make contribution to the second. Okay. Exactly. Yeah.
Okay. Thank you.
Yeah. Mm-hmm. Marilyn, did you have any questions? Okay, all right. So I'm gonna go ahead and close the call then. And so if you have any questions, just email me, and I'll get back to you as soon as I can. Right.